the story of Richard Feynman trying to cut his
No, you didn't.
Once upon a time, Richard Feynman was working in a restaurant. You know what his job was? His job was to split beef down the middle with a knife. So every day he would split beef. And he was like, you know what? This is slow. So you know what he did? He taped the knife up so that the blade was like this way, the sharp part was here. So he could like do this, just split the beef like that. And he was like, oh wow, this is so much faster. Hey boss. And then he got cut off like this. And then he gets fired.
As you would.
Of course. Did I tell you about the time Richard Feynman filled his room with ants?
No.
He filled his room with ants!
And yes, Benjamin, and yes, my wife read it out. Nothing about me wants to hear this out.
He filled his room with ants!
I don't care.
You should. It's amazing. Richard Feynman is amazing. I love Richard Feynman. Ah, this is not what I wanted. Look at what happened the first time I tried to convert it to a text file.
What?
It's what happened when you tried to convert a Google Sheet to a text file.
Why did you try to convert it to a text file?
Because it said to. It said auto convert it to a text file.
Yes, and that's incredibly. You have to type it out.
I didn't want to.
So you're trying to convert doc to text?
Sheet to text. It's okay, we figured it out. We downloaded it as a bunch of different things and kept switching it through different things, and then it finally came.
You probably spent so much work if you had spent typing that it would have been taking less time.
You are correct, sir.
Individuals are the only ones that can convince themselves doing a stupid idea is better than doing a smart one.
What other Richard Feynman stories are there?
Not ones I want to hear.
Hi everyone!
Hello! Did I tell you about the story of Richard Feynman and Queen Elizabeth?
Stop.
I got 26, probably close enough.
Sticks and stones will break my bones, but ModPhys definitely will.
Okay. Raise your hand. So, you got me? Alright.
There's Nino.
Friday work? Enough? Is it Friday night?
Being a relativistic.
There's you guys like a thing to Brad to do on Friday
I'll be
night?
jumping on
Maybe true.
Maybe true.
Oh no. Oh no.
What?
Oh no.
Yeah.
I mean, I can give you, if you really want it Friday night, wouldn't you rather just get it over with?
I have a history project due tomorrow.
I have so much.
What history class do you
I
have?
don't really care.
Conflict.
But I just feel like a Friday deadline would really suck. I would want it.
Hold on, you know where the drive in like Saturday?
Yes.
I can tell you this, in a few days I assign you the muon detector. Right? And I'm not letting up the physics homework. There's one more quiz, one quiz in the month of November, most of this project work. Okay? So I can tell you other things. I don't care particularly about the deadline. Except for one thing, I need to turn this around to you in time, right? Because you need to be able to make changes for the final project, right? So I can't take anything ahead. Like, you know what? I think it is better not to draw out the pain. How about we go? I can give you a Friday night. I think that should be enough time. I think people are working hard on it. You should be mostly done. It should be fine. Your apps are done. Or not due till the 15th or the December 1st or whatever, right? So it should be fine. Or your things. So let's not throw this out. Today we're doing something very special. People laugh. You know, right? Yeah, crazy, right? Okay, so lab apparatus is over here, half this.
How are we gonna be alive about this?
So, here's basically how it works.
So
Okay?
so
And in fact, you guys got paid. We don't know a lot of time on the live on during this. We need to live on during this period. So, here's how it works. Discovered in the late 19th century, and if you take a piece of metal, wow. Discovered like this
Wait, make it in a basket. You need to throw it.
Just open your mouth.
no cracks, something else.
By the way, you don't have to have the lead tungsten with every other thing.
Well, let's put it this way.
Wait,
Let's
well,
connect
like,
this
just
to
have
our
people
thing.
use it.
You guys may not know how to read
Forgot how that works.
Say you have a piece of metal here, okay? And you connect it to an ammeter which measures current, okay? This guy measures current. Then you shine light at this thing. You know what happens? You start reading something. You start reading a current. You shine light that starts reading current. Now, current is a flow of electrons, is what it's measuring. And so, what you deduce must happen. The light is knocking electrons off the metal. That's right. So the light hits the metal, it knocks off electrons. The electrons then complete the circuit, and you read a current.
This is going to involve the slit thing that we talked about at the end of class last time.
Does it involve the what?
The slit.
Not directly.
Okay.
I thought you said the slut thing. That was really very good experiment. So
You get really deep into Richard Feynman.
So now with these electrons, which they have, this is referred to because it's light that then generates electrons. We call it the electric.
Wow.
Okay. Because the light generates electrons. Okay. Now, what would you like to measure about the electrons?
How their days are going.
We already got that. The magnitude of the electron. What's that mean?
They're
You
spinning.
measure the current, we got that. What would you like to measure?
spin.
What would you interested
No.
to know about the electrons, like sort of the more individual level?
Their spin.
No, I'm not doing that. This is the 19th century. What would you like to know about the electrons?
Number of them.
I really wanted to.
Sure, their energy. Right? That sort of thing we measure about particles. So you say, how much energy has come off? Well, they come off with different energies. Not so surprisingly, right? Some have higher energy, some have lower energy. So it would be a sensible energy that you might want to know.
Minimum.
Yeah, how about the maximum energy? So you can also do average, but maximum turns out to be easier to measure. So we're going to look at the maximum kinetic energy of the electron. Reasonable thing to measure, right? You'd want to know about that. How do you measure that? Well, clever idea. You take this thing and you attach a battery. That's a symbol for battery. I'll label it battery.
What is that the symbol for battery?
Fantasy
That's a symbol for battery.
Why?
Why? Because that's the positive end, that's the negative end.
Wait.
Well, come on, why would any symbols mean anything? Come on, because that's pretty cool enough.
Because they look similar.
So, I mean, why is this symbol for wire?
Because it looks like a wire.
So you have a battery here. Because batteries are originally a tank of chemicals with plates in them, right? So it looks kind of like that. Okay, so you put a battery on this thing. You use a variable voltage source. Okay, so a battery you can turn on and off. What would the battery do? Well, it would put a positive charge here and a negative charge here, the voltage difference. Okay. Now, if you have a positive charge here and a negative charge here, what does that do to the electrons going across? It will repel them from this side and attract them to the left side, right? So what will happen to low energy electrons?
They'll get pulled back.
Low energy electrons will get pulled back by that electric field, right? What will happen to high energy electrons? They'll still make it, right? Because they have enough energy to make it through that voltage difference and they can then still keep going. Okay? So, therefore, you take this thing and it's a variable voltage source. So, you turn it up a little bit, what should happen?
Fewer and fewer will come, but they'll be higher energy.
Fewer electrons will get across, which means, what will you read here?
Higher and higher energy?
Lower
A volt
current.
higher.
Lower current. This measures current, which is how many electrons. So fewer electrons make it through, therefore you get a lower and lower current, right? Because you're getting fewer of them through. They are higher energy electrons, but not as many are getting through. That's what current measures. So as voltage increases, that's from the battery, then current decreases. Yeah.
Why don't we stick something in there that measures the voltage as well, so then we can just get a compare.
We have the voltage right here.
We're the ones adding the voltage.
Voltage
We
is
can know how much.
something we apply, right?
No, I mean, so when the electrons go in and complete the circuit, we're measuring the current of the electrons, right?
Right.
So we could probably also measure the voltage of the.
It's way too small.
Okay.
Yeah, that's actually the thing is this current is tiny, and it's much easier to measure the tiny currents than the tiny voltages.
Okay.
Good point. No, this is how we have to do it because it's hard to do it the other way. It doesn't knock off a lot of electrons, okay? It only knocks off a few. This is measured in nanoamperes. So not very many electrons. Okay, but as you increase the voltage, the current goes down. What's going to happen eventually if you keep turning the voltage up? Eventually, the current goes to 0, right? So when current reaches 0, the voltage is called the stopping potential. Potential is another word for voltage. So stopping potential means the voltage you need in order to stop the current, right? Now, if you keep turning it up, of course, it'll stay 0. It's not going to go negative. It doesn't make sense, right? It's going to stay 0. But the point where you just when current reaches 0, there we go. Just when you get it to just reach 0, that's your stopping potential, right? We will call the stopping potential V0. Good name for it, right? Okay. Now there's a simple equation to figure it out from here. The maximum kinetic energy, Ke max, is equal to the stopping potential times Q, where Q is the electron charge, 1.6 times 10 to the negative 19 coulombs. It's a constant. So once you measure the stopping potential, it is very, very easy to get the kinetic energy. Sorry. 1.6 times 10 to the negative 19 coulombs. It's the charge of an electron. Okay? The reason for this, you take E and M, you learn all about this stuff. Okay? But we don't need to worry about all that. All you really need to do is this equation. So what we're going to do is measure the stopping potential. Okay? Which means you shine a light in, right? The thing that does here has to take this photoelectric effect and to actually measure it, you got to amplify it because the current is way too small. So there's a current amplifier in it. And so basically these boxes that do it, like this here, these little boxes that say photoelectric effect on them, are basically photomultiplier tubes. Same as they use in other emitters, right? They're not exactly the same, they're the same basic technology. So these are PMTs. They're photomultiplier tubes that take light and convert it into electrical signal. Yeah, get it? So that's the photoelectric effect at work. So now what you're going to do is you'll shine a light, and then you're going to turn off the lights so that you can localize the light a bit. You'll shine a light into the hole at the end of the box here. Okay, and then you will see on it a current will go up. Right, there's a little meter that has a current. The currents will go up. Okay. And then you have a knob that controls voltage. And if you turn up the knob, what's going to happen?
It's going to go.
The current's going to go down, all right? And then you need to get the current to reach 0, and just adjust enough to reach 0. When you do that, then you'll have the stopping potential, which this thing is plugged into a multimeter over here, which measures the voltage. Okay, for some reason it doesn't read it out on there. I don't know why not. So you plug it in here, it'll be at a voltage for you. And so that voltage you read out. So you turn it up until you get the current down to 0, and that voltage that's on the voltmeter is called your stopping potential. That's the stopping potential. Okay. So you turn on the light, you turn the thing up till it reaches 0, and then you look over what it says on here, and that's your stopping potential. Okay. And that's what we'll measure. Now, you've got to have a changing variable here, right? So, what is something you can change about the light? The brightness, right, or the intensity. Okay, good. So, make a prediction. As intensity increases, what would you, intensity increases means you have brighter light, right? More energy coming in, so then therefore what would you expect to happen with the maximum energy in the electrons?
It's going to go up.
It would go up, as I said, yes, it will go up, right? Does that make sense? You can do it more rigorously with the maximum equations and stuff, and you'll get that answer. Okay? You'd expect the intensity increases and the maximum kinetic energy increases. Anything else to change about the light? Okay, the wavelength, what's that mean for light?
The color.
Color, right? Change the color. We, for whatever reason, say frequency. I don't know why. They're for light, they're very closely related, right? Because you guys remember the basic equation for waves? Velocity equals wavelength times frequency. Remember that? If you don't, please remember that. Write it down, I'll need it. Velocity equals wavelength times frequency. It's very easy because for light, the velocity is c, right? So wavelength and frequency are just a simple inverse relationship. So it's no particular reason to use one rather than the other, but for whatever reason you talk frequency. Okay? So different frequencies are different colors of light. So if you change the frequency of light for the same amount of light, you change the frequency. What do you expect to happen to the energy? What? No, I said the same amount of light.
Because when the speed of light, right, that doesn't change.
Right? It's the same amount of light, just a different color. And then you're like, okay, then you would say
wavelength
maybe max
invariant?
I think
doesn't change.
But what is
All right, good. So I want you to test this. So you can do 3 different brightnesses of light and 3 different frequencies. Yeah.
I have a question about wavelength.
Yes.
How is it in its like relativistic perspective?
Wow. Sucks. No, it's fine. It still works fine because this equation works fine because c is constant, right? So there's nothing funny here. You do have Doppler effects and stuff like that that affect it, relativistic Doppler effects, like we did with William Howard Taft.
He's saying,
But I mean, like,
relativistic speeds want the wave like shorten.
If you're in a different reference frame, the wavelength will change. Yes.
Okay.
So will the frequency, right? But this equation won't change, right?
Yeah.
Yeah. So they change in the exact opposite ways, which is exactly what should happen, right? Because length and time change in opposite ways. So it works. Okay, good. These here, Dr. Hawker neatly organized them. These here are 3 different color filters. Okay, they're so you can each have 1 of each color. I think we have enough. Yeah, looks like we have enough. And then, so I want you to try 3 different brightnesses and 3 different filter colors. Now, the brightness is a little bit hard to put an exact number on, and we're not going to try. Okay, make sure there are 3 different brightnesses. Okay. I did it as a rule, as a like rough thing, just say write down the voltage that you were using. No, but like the point is just make sure there are 3 different brightnesses. Is the main thing. Okay, that part you can tell easily. Now, these light bulbs are regular incandescent light bulbs, meaning they can burn out. So don't do it. What does that mean? Keep the voltage knob all the way down, which they are right now, and then turn it on, and nothing happens. The voltage knob is all the way down. Then take the voltage knob and turn it up gently, and then the light will turn on. And don't turn it on too high. Okay? When all the lights are off, it'll get fairly bright. As long as you can get a decent signal, you can get 3 distinctly different brightnesses, you're fine. Okay? And then when you're done with it, turn the voltage knob off and then turn the power supply off so that you're not accidentally turning it on at the wrong time. Okay? So you're not going to shock yourself with one of these, but I don't want you to blow up the light bulb. Okay? Okay, we have 6 stations. The lab's on Google. So, wait, is the lab on Google? The lab is on my computer.
Want to be my partner for a while?
What are we putting out?
Okay, we got our computers. We have 6 stations, so there's 25 people in this room, so you figure it out.
You figured it out.
Jello.
No, I am not Jello.
Be late.
Eli Whitney.
What?
Okay, so like I was saying, the lab is now on Moodle. It's under homework, because like whatever.
He lied to us.
So, yeah, so go ahead and pull the document up. The second page is where your data table is. Just got to enter that in. And that's what we want to get done today, okay? It should take like half an hour, right? But we have to kind of move. So, if we can start kind of moving. Okay, so the stations are there, this would be on this side.
Nope.
And then
I don't want to work with you,
there.
Benji.
Yeah, so the 6 stations. So, my
Just messing with you.
I'm uploading it on the Google Drive.
I'm just going to enter it into my computer.
Well, that's not. You'll put it on the Google Drive later.
Fine.
Yeah, you do it.
I will. Thank you very much.
Yeah.
Narnia.
What do you? This isn't Dead Poets Society. You can't just stand on chairs.
Yes, I can.
No, well, I mean you
I
can.
can definitely stand on chairs if I want to.
Okay, Dead Poet Society, Robin Williams.
Alright, I'm ditching you.
Wow, ouch. Well, ouch.
Give me a minute or two to get
Just no.
then I will.
That's fake.
Alright. Make sure all the switches are off.
Yeah, filters.
Turn all the switches on.
I don't know. Are they? I don't know.
I think
Can
that one
you?
looks like it's off. Okay.